ลืมทำไมมันเป็นโมเมนต์ที่แบบสำคัญมากเลยใช่ป่ะดูชยุทธพลนี่นอนอยู่ยังลุกขึ้นมาดูอ่ะขอผมก็เลยมันจุดไคลแม็กซ์หรือว่าจะอวสานหรือว่ายังไงอันนี้หรือเปล่าอ๋อแอนิเมชันสวยอย่างนี้ใช่ป่ะTest 1 2 3 ต้องอธิบายด้วยผมว่าคุณดูอะไรที่มันไม่รู้เรื่องบ้างก็ได้นะรู้เรื่องมากปวดหัวครับสมมุติเธอสมมุติคุณไปขอผู้หญิงแต่งงานอ่ะกำลังจะสวมแหวนให้เขาเงี้ยบอกขอคำนวณแรงดันเข้าไปหน่อยอันนี้ได้ไหมแรงดันเข้าไปในนิ้วอ่ะคุณไม่ต้องนะครับเห็นปะมันไม่ต้องเป๊ะรู้ทุกอย่างอะไรครับทุกจังหวะครับเห็นปะ
Okay, good afternoon everyone. Welcome you to SCI33205 or 606. That's physics number 4 or number 5. Okay. It seems that someone is mixing and he just sent or he sent for water. คุณยวีมีไข้คุณยวีผมต้องไปแก้สาดูงานปริญญาโท Okay, anyway, we're gonna check it again. M604 right? Play.
เอาศิวกรตะกี้ก็ยังเห็นตัวเป็นตัวจริงอยู่นี่เลยตะกี้เลยใช่ป่ะเหรอเร็วมากนะครับโอเคโอ้ผมเหรอเห็นตัวเป็นตะกี้นี้ไปแล้วนะครับหายไปแล้วไม่ได้บอกอะไรผมล่วงหน้านะเพลงนะไม่เป็นไรโอเคครับปะนิชีครับแล้วก็กิจผู้ทิพย์ครับกิจผู้ทิพย์จะอยู่ทางเนี้ยนั่งกับผมเนี่ยอะไรแล้วแอบเซนไว้นะครับคารานะครับอยู่นี่ครับก็ตะก้อนมาแล้วศิลวิทย์สุขีนี่นะก็ลาวิพลครับลาวิพลทีมศิลป์ครับทีมศิลป์ฮะนอนอยู่เหรอแล้วทีมศิลป์นอนด้วยเหรอปกติเขาจะไม่นอนไม่เคยเห็นนอนสักทีไม่เป็นไรครับรบกวนเพื่อนเหนื่อยจากเตะฟุตบอลนะเต็มภูมิครับเต็มภูมิUniversity ที่ทักครับผมแล้วก็พิชานันท์อะไรกันพัฒนาคินศิลวิทย์โพคิดครับผมทีนะครับอยู่นี่นะครับแล้วก็ธนาวิทย์ครับโอเคครับสนุดีครับเอาละโป๊กเกอร์เตรียมตั้งวงแล้วได้เวลาแล้วนะครับรัตนาครับโอเคครับแล้วก็ศิวกรไปอันนี้เขาเขียนว่าอะไรมองไม่เห็นไปตรวจสุขภาพเพื่อยื่นมหาวิทยาลัยโอเคเขามีรูปแล้วไงของแท้เขาที่แล้วตลาดเฮลเชงไม่ใช่เหรอเขาก็มาหาอะไรอยู่นะก็ลาเหมือนเดิมโอเคนัทพลแอลก็ชยุทธพลโอเคนอนต่อไปนะครับแล้วก็กรรุ่นครับกรนี่สามารถรับจ็อบพิเศษได้นะคุณเห็นแบบเวลาเขามีที่ท่องเที่ยวชายหาดแล้วรับจ้างวาดหน้าคนจ้างวาดที่แบบว่าให้หน้าเหมือนอะไรอย่างเงี้ยคุณเคยทำปะวาดไม่ได้ก็อย่างนั้นผมเคยเห็นพี่สาวผมไปเที่ยวแล้วเขาก็ได้รูปอย่างนั้นมาอยู่ อ๋อโอเคครับพิโชตครับพิโชตพวกนี้นี่ University Interview นี่คือเขารับคุณหมดทุกคนเลยใช่ไหมเขาไม่เอาผมเหรอฮะชานนท์ฮะติดออฟเฟิร์ด
ตั้งแต่คุณพักผ่อนแล้วเนี่ยไม่เขาไม่ติดอะไรเลยตอนนี้เขาจะไปขอทานไม่เขาก็ตั้งใจอยู่นานว่าเขาจะเรียนราชพัฒหรือว่าไปต้องเรียนที่มอลาอ๋อ
ไปที่ไหนนะไม่รู้จัก
เทถวายจาน
โอเคถวายเขาจะโดนยึดที่อยู่ไม่ใช่เหรอหรือว่าได้โอเคทำผมไม่กล้าใส่เสื้อช็อปเลยนะตอนเรียนชานนท์อยู่นะครับก็กมลสิทธิ์สุภชีกมลสิทธิ์ไปไหนแล้วพี่เบิ้มผลอะไปไหนแล้วพี่เบิ้มสุภรัตน์ตื่นมาแล้วครับณัฐพลเอ็นย้ายกลุ่มไปนั่งนู่นแล้วณัฐพลเอ็นคุณย้ายไปนู่นแล้วทามครับไปญี่ปุ่นอ๋อแข่งภาษาญี่ปุ่นที่อยู่ในใบอันนี้นะครับใช่ปะเอาแล้วคุณก็ไม่แจ้งผมอะมาอะไรตอนนี้เนี่ยใช่เร่งด่วนก็ต้องแจ้งถูกต้องตามแล้วคุณยาวมาขนาดนี้ต้องให้ผมไปลื้อแก้อีกเหรอโอ้มันหลายอย่างนะมันแก้ไฟล์อัปโหลดใน Google Classroom คุณเร่งด่วนคุณก็ไลน์มันอินเทอร์เน็ตมันก็มีทุกหัวและแห่งประเทศไทยหรือเปล่าครับมันต้องมีทุกที่ดิเดี๋ยวของไทม์นี้นะ Activity นะแล้วก็ณัฐดลครับณัฐดลฮัลโหลโอเคครับอาริยวุฒิอยู่นี่นะครับอาริยวุฒิคุณตัดผมแล้วเหรอเจ๋วเลยตอนไม่ตัดนี่แบบเหมือนใส่หมวกกันน็อกตลอดเวลาเลยเจ๋วเลยผมชอบอันนี้ไปเพราะตัดเพราะไปรอดอหรือว่าเอาเพื่อนเขาไปแล้วไม่ใช่เหรอไปรอบสองได้ด้วย
เขาไปแลกเปลี่ยนมาก็เลยไม่ได้เรียนหรอก
อ๋ออันนี้คือจะเป็นกับรุ่นน้องป่ะม.5 อย่างนี้เลยป่ะ
ใช่
อ๋อแล้วอยู่ปริญญาตรีคุณก็ต้องไปเรียนรอดออีกเป็นไม่ได้ด้วยเดี๋ยวแต่ปริญญาตรีเขาจะไม่หยุดวันพุธไม่ใช่ไม่หยุดวัน
ผมอ่านของมหาลัยเขาบอกให้สมัครได้ก็ไปวันเสาร์
อ๋อไปวันเสาร์ได้เขาจะไม่หยุดวันพฤหัสให้เรานะมหาลัยเขาจะเปิดเรียนปกติเลยเจ๋วดิคุณจะเป็นประสบการณ์พิเศษนะครับภูริศักดิ์นะครับดีครับ
ล่าสุดผมไปตอนไปรอไปเข้าเวรยังเห็นที่มสวมาเรียน
เหรอพวกอยู่ปริญญาตรีอย่างเงี้ยนะครับ
เขาบอกให้อยู่คณะ
เอนจิเนียริ่ง
ใช่
อ๋อเหรอมาด้วย
ผมเข้าเวรกับเขา
เข้าเวรกับเขา
ใช่เข้าเวรเข้าถังน้ำ
โอ้โห
เข้าถังน้ำ
อ๋อมีคุณค่ามากนะถังน้ำเดี๋ยวถังน้ำหายไงนะมันเป็นกิจกรรมอะไรที่มันสติวปิดหน่อยล่ะของรอดอเนี่ยวัดสันตพัฒน์อยู่นี่ประมาณนั้นหอบลุกอยู่อย่างนั้นนะแล้วก็ให้คุณกินฝุ่นไงครับเดี๋ยวกมลสิทธิ์เอาไงนี่พี่เบิ้มผมไม่มีอะไรร่องรอยผมเขียนเป็นแอปเซนต์นะแอปเซนต์นะครับโอเคป่ะเมื่อเช้าก็ยังเห็นตัวอยู่ไม่แถวเมื่อเช้า
อะไร
M604, right? This one.เดี๋ยวมีอะไรมากกว่านี้ไหมผมก็ลืมไปแล้วเมื่อเช้ากลุ่มนี้ แล้วก็คุณวีในห้อง5นะครับห้อง5มีไข้อารมณ์คนเซ็นก็เข้าออกๆนะทำให้คุณลาได้บ้างลาไม่ได้บ้างครับคนเซ็นให้เนี่ยปัทดลห้อง5นะไม่เกี่ยวนี่ก็นัทนนท์ห้อง5กันเอกป่วยก็ห้อง5ไม่เกี่ยวกับเรานี่ไม่ใช่ม5ไม่เกี่ยวครับโอเคเรียบร้อยครับ Okay, let's continue our stuff that the nuclear physics in this diagram, right? We arrive at the this point, right? Bismuth, which has 83 protons and 212 nucleons. There are two ways for bismuth 212. The first one is that it doesn't discard any nucleons at all, and it's going to be polonium 212, but it just loses one proton. Is going to be polonium. No, it has one more proton, right? When you go right, you're going to have one more proton to the right, and another possibility is to go to this one, right? Thallium, right? As the Silavit Suki suggested, it's thallium. It's a chemical element, right? That has 81 protons. Okay, you're gonna lose two protons, and you lose 4 nucleons. Okay, and then you reach lead, which has 82 protons and 208 nucleons, and that's this one, right? Thorium series. Okay. We have to say thank to the physicists that collect all this information. Okay, yeah, very good. They collect everything to us, and I think this is quite dangerous, right? Because you're gonna absorb all the time several rays like alpha rays, beta rays. It's dangerous actually, but they record it for us. Okay, yeah, that's all for the beta decay. At the end, it's combined with the alpha decay as well. Okay, in the nature, the decay process can include both alpha decay and beta decay. It depends on which situation we're gonna reach. Now let's move to the last type of the decay, and that's gamma decay. Okay, in this process, we didn't have the particle at all, any particle. It's only a photon emission, okay, but it has very large amount of frequency, high frequency, and large amount of energy. The nucleus undergoes a radioactive decay that causes alpha emission and beta emission. However, the daughter nucleus often remains in unstable state or an excited state. This appears to be unstable, and the daughter nucleus will undergo another decay to a lower energy state, perhaps to the ground state, and caused by the proton or the neutron in the nucleus, because there is still vibration caused by protons and neutron. that move from a higher energy level to a lower energy level, and that will cause the emission of extra energy in terms of gamma ray photon or gamma, which is denoted by gamma. So there are two names, gamma ray photon, full name, or sometimes, simply speaking, we're gonna say gamma. The typical gamma energy is in the level of 10 kilo electron volt or to 5 mega electron volt, which is very large amount actually. โอเคกระบวนสิทธิ์มาแล้วนะ สวัสดีครับ 604 ไฟล์ใหญ่นะครับ รูปเยอะนะครับทำให้อัปโหลดไปช้านะครับ Okay, that's all. Okay, yeah, gamma is high energy emission actually. Let's talk about the detail of this process. Gamma decay can take place after the alpha decay, which is given by the following. When you start with radium 226, okay, radium has 88 protons, which is quite a large nucleus actually, because it's bigger than bismuth 83, right? And you're gonna end up with radon 86, okay, 86 proton and 222. But it's written with the star like this, okay, or complex conjugate. But this doesn't mean complex conjugate at all. It means the nucleus is still in excited state, okay, when we have the star operator like this. It doesn't mean you have to change the symbol or the sign of in front of J or square root of -1 or not something like that. It's only the meaning that is the symbol of excited state for that nucleus, for that atom. Okay, and you will have here also alpha 42, right, which is alpha particle. This is helium 42 actually. And the next step, the additional step, additional process that you have apart from the former or the typical alpha decay is the following. The radon with the star, okay, will be decomposed into simple radon without star and the gamma symbol. Gamma symbol means the gamma ray that we can have from this process. Okay, so it's not as usual. Okay, we don't have radon without star as usual. It turns to be radon with star. Okay, and the star nucleus would calm down. Okay, to the normal state. Okay, or the ground state of that nucleus, and we have an additional energy term which is the gamma. Okay, gamma doesn't have any nucleon or any proton. That's why we don't have the number on the left side, whether it's superscript or subscript here. Okay, gamma 00 actually. So it doesn't have any mass at all. Let's consider the total released energy, which is 4.871 mega electron volt or 4.685 mega from equation 68. In the following, here in that in both equations, radium can reach the radon with our star. Okay, and we're gonna get only alpha particle. And another type that we have recently is the process that we reach radon, okay, which is in the higher energy level, but with star. Okay, this is still in unstable state with star, right? And we lose 2 protons and we lose 4 nucleons, and that's why we get radon. But the energy here is higher than normal radon. In order to cool down, radon will emit the gamma ray, which is a kind of photon, and its energy state will be lower to the typical one. If you reach radon immediately without any exciting state, the energy difference is 4.871. But for some nucleus, they don't reach the normal or the ground state immediately. They're gonna reach first the exciting state. This will cool down with only a 4.685 mega electron volt, and when it turns to be normal state, it's gonna emit the gamma array with the energy 0.186 mega electron volt. Okay, this is the energy gap. Okay, this energy gap will be allocated to gamma ray immediately. Okay. Now let's consider the gamma decay that causes change in. This gamma process doesn't change any mass number or atomic number at all. So A and Z for that nucleus, like radon star and radon without star, the number of nucleons and the number of protons are the same. Okay, 222, 222, and 86, 86. Gamma decay that happens after the beta decay is also possible. An example is the following. You start from boron 12. Okay, the closest isotope is one of the closest isotope is carbon 12. Okay, carbon, as you can see in the wood and many stuff around us. And one of the neutron turns to be proton, right? And in order to cancel the additional positive charge, it's going to emit also an electron. This is beta minus process, and we have also the electron antineutrino, whose mass is still unknown to us. But the carbon here is still in an exciting state, okay, with the star symbol here on the superscript on the right. And the carbon will be cooled down to a typical carbon, but to be cooled down, the carbon will emit the gamma ray, okay, which is a kind of photon here. Okay, now let's talk about carbon dating. What does that mean, dating? Dating doesn't mean you want to ask for the love from another gender. Dating is something about to calculate the date or the age of an object. Okay, dating is in a different meaning. As mentioned earlier, at the beginning or in the introduction of this chapter, carbon-14 is a kind of unstable isotope of typical carbon. It's a radioactive isotope, actually, of the carbon nuclei. Carbon-14 is unstable with a long life, with a long half-life, and it's typically created in the high uh, high level of our atmosphere. I forget the name, but we will see it later in some slides. Okay, the half-life of the carbon-14 is 5,730 plus and minus 40 years. Okay, and in our world, let's talk about the whole environment that we are living in. In our world, the carbon-14 is created by cosmic rays in this figure. Okay, the cosmic ray comes from a deep space, from outside the world. Okay, and it has high energy particles from outer space. From the okay, the cosmic ray just hit the nitrogen. You know that in our air, the atmosphere around us contains the air, right? And the air has the nitrogen. The nitrogen has the isotope of 14, okay, 14 nucleon. And when it hits the neutron from the cosmic rays, cosmic ray will create a neutron. Neutron will hit the nitrogen 14. As nitrogen 14 has 7 proton, and one of the proton will be discarded from the nucleus. Okay, one proton is will go away from the nucleus, and that's why we have this thing. And this neutron will stay in state of the proton, right? Yeah, proton just go out. Okay, we get something like this. Okay, and you can see that. Yeah, we have 7 proton, and neutron will stay in the place of proton. We get proton out of this process. Okay, this interaction takes place in the upper atmosphere. For example, in troposphere and stratosphere. Simply speaking, it's around 9 to 15 kilometers above the ground. Okay, we're gonna have this process, and okay, that's the origin of carbon-14, and it continuously occurs in this higher level of our atmosphere. The ratio of carbon-14 and carbon-12 is constant, and it's approximately 10 to negative 12, which is very little. In the nature, actually. Okay, so let's have a look at this picture. The cosmic ray, which contains high energy proton and alpha particle, is going to reach the atmosphere, and this will create the neutron. Okay, neutron will hit the nitrogen 14. หมดเวลาแล้วเหรอหนึ่งข้ามครับเคยผมกำลังเร่งเดี๋ยวจะไม่ทันครับเราได้เท่าไหร่แล้วเนี่ย79จาก148นะครับได้ประมาณครึ่งหนึ่งครับโอเคokay yeah, you will get 1 proton. Okay, and the losing a proton and gaining a neutron converts nitrogen 14 to carbon 14. Okay, we get carbon 14 right here. And this is an attractive nucleus. It will be combined with oxygen. Okay, and it can be carbon monoxide molecule or even the carbon dioxide molecule. Carbon monoxide get oxidized. Okay, it absorbs one more oxygen to be carbon dioxide, right? And carbon dioxide will stay lower, okay, because the molecule is heavier, and then the plant we absorb the carbon dioxide, right, as one of the its ingredient, okay, to cook as the food, and then it will absorb carbon dioxide and sorry, together with the photon from the sun, the plant will get the energy from the carbon dioxide and once the plant stay on earth, on the ground, the animal will eat the plant, right? And some parts of that, we also have the plant, right, on earth, like vegetables and so on. Carbon-14, of course, will be inside our body, not only human, but also animal. Okay, animal will have the plant like grass and so on, grasses. Carbon-14 will be absorbed in animal body like cow, horse, and so on. But of course, you know, beef is one of the favorite food to human, right? You prefer steak, right? Whether it's you don't like steak, right? Okay, but some of you, right, prefer the food in terms of steak. A steak is made from beef, right? Beef contains carbon-14. Once you eat steak, carbon-14 will get into your body. Okay, even not only that. Okay, when you breathe in, you inhale. Okay, your inhalation will get the carbon-14 as well. Okay. This is the formation of carbon-14 from the cosmic ray and its absorption in the nature. So in our body, we would have also carbon-14. So don't be afraid of radioactive because your body also have carbon-14, which is a kind of radioactive mechanism inside your body. Okay, nitrogen. Okay, from the interaction in the upper level atmosphere, we heat the nitrogen 14, and nitrogen 14 will be transformed into carbon 14, which is a radioactive isotope, and one of the outcomes is the proton. Okay, carbon 14 will disintegrate to lower nucleus like nitrogen 14. Okay, it's called beta decay. The half-life is 5,730 years. Okay, which is very long time actually, long period. And we're gonna get because neutron turns to be proton, we're gonna get also the negative particle. This is electron, and here is electron antineutrino from this process. Okay, this one เป็นเบต้าไมนัสหรือเปล่าเบต้าไมนัสนะเพราะว่าเราได้อิเล็กตรอนไงถ้าพลัสมันจะเป็นโพซิทรอนดูอีกอย่างหนึ่งก็ได้ก็คือถ้าเป็นแอนตี้นิวทริโนเนี่ยมันจะเป็นไมนัสเห็นไหมถ้าเป็นนิวทริโนธรรมดาที่ไม่ใช่แอนตี้พาร์ติเคิลมันจะเป็นพลัสนะครับโอเคthis is the generation of the above process is generation of carbon-14. The lower one is the disintegration or the decay of carbon-14 that takes place simultaneously, okay, at the same time. Another one is the condition of carbon-14 organism. Nitrogen absorbs neutron and it turns to be carbon-14 together with proton. And carbon-14 will be disintegrated into nitrogen-14 again, together with electron and electron antineutrino. You know, this process can take place because it absorbs also the energy from the deep space, okay, and this one will release the energy to rust. And this process will turn away, turn around all the time, okay? Because nitrogen 14 will go higher, okay, because the mass is lower. And when both processes take place simultaneously, human can find the ratio, okay, molecule of number of mole of carbon 14 is million times the number of moles of the carbon 14. And when we pass it away, the number of molecule of carbon 14 will be less, right? From this process, we destroy the carbon 14, so the number of moles for carbon 14 will be smaller and smaller. So the portion of carbon 12 will be greater than carbon 14. Okay. Now let's talk about the way how clever people adopt this process in order to determine the age of the living or the dead organism. Okay, all living organisms have the same ratio of the carbon 14 to carbon 12 because they continuously exchange carbon dioxide with their surroundings. Okay, this will take place when you are alive, okay? But when the organism dies, okay, when we pass away, our body doesn't inhale anymore, it doesn't breathe in, so there is no channel, there's no way carbon 14 will get into our body, so our body no longer absorbs the carbon 14 from the atmosphere. But we still have carbon 14 inside our body. Carbon 14 will be decayed, okay, will absorb decay with a half-life around 5,730. For example, if in our body has the carbon 14 of 1 gram, and if you let your body stay on Earth for 5,730 years, the 1 gram of carbon 14 inside your body will be reduced to only 0 or 1.5, right? 0.5 gram only, okay, for this amount of time, which is quite long. So the ratio of the carbon 14 to carbon 12 will decrease as the result of the beta decay by the carbon 14, okay? Even you don't want, but this will occur in nature, by measuring the proportion of carbon 14 in the remains, we can determine how long ago the organism died. So you can calculate, right? If my body doesn't lose any mass at all, and someone discovered only 0.5 gram inside my body, it means that my body has already passed away for around 5,730 years. Okay, สมมุติผมเสียชีวิตแล้วเส้นผมอะไรผมไม่ร่วงเลยนะมวลผมก็ไม่หายสักนิดเลยสักกรัมเลยนะแล้วเขาก็มาขูดเนื้อดูนะครับแล้วพบว่าคาร์บอน14ของผมมันลดลงไปเหลือ 0.5 กรัมนี่แสดงว่าร่างกายผมเสียชีวิตมาแล้ว 5,730 ปีซึ่งพวกอะไรนะฟาโรห์อียิปต์เขาก็จะแนวนั้นป่ะที่แบบว่าหาว่ากษัตริย์ของเขาเนี่ยเสียชีวิตมาเท่าไหร่แล้วใช่ป่ะเพราะว่าไม่ได้ว่าศาสนาครับเพราะว่าโซนนั้นนะครับก็คือเขาเชื่อถือใช่ไหมว่าคนเสียชีวิตไปแล้วจะฟื้นใช่ป่ะเขาก็พันร่างกายของกษัตริย์เขาไว้เพื่อว่าจะได้ฟื้นกลับคืนชีพเนาะถ้าคนธรรมดาชาวบ้านสามัญเราคงไม่มีใครสนใจอยากได้ให้เรากลับคืนมานะเขาก็ปล่อยฝังดินทิ้งไปนะครับแต่ถ้าคนสำคัญอย่างเป็นกษัตริย์เนี่ยเขาก็จะรักษาไว้เพื่อให้ฟื้นคืนชีพกลับมาแต่คุณคิดว่าเป็นไปได้จริงไหมผมก็ไม่รู้เหมือนกันนะครับนักวิทยาศาสตร์ก็ใช้ ตรงนี้นะครับในการหาอายุของพวกฟาโรห์นะครับที่เก็บในสฟิงค์ที่อียิปต์นะครับเดี๋ยวคุณโตแล้วทำงานมีเงินเยอะเดี๋ยวคุณก็ได้ไปเที่ยวอียิปต์นะครับเพื่อนผมก็ไปเที่ยวมาแล้วนะครับโอเค Okay, it's possible to determine the age of the material by measuring its activity per unit mass. As a result, the decay of the carbon-14, you know activity, right? It's the decay rate, actually. Now let's consider the first example about carbon dating, which is important. Okay, it's going to be included as part of the final exam. I'm not sure whether the camera works well or not because the battery is quite low from the morning. Okay. Yeah, great. นะครับสมาร์ทโฟนเดี๋ยวนี้เขาจะแบบว่าเขาจะแบบบล็อกไม่ให้ชาร์จเพิ่มเนาะเพราะว่าการแบตเตอรี่มันร้อนนะครับทำให้ผมไม่สามารถชาร์จเต็มได้เกิน 80 นะครับแล้วเกรงว่า 3 ชั่วโมงจะไม่พอใช้ของเรานะครับฮะโอเคครับ20กิจภูทิพย์นะครับ604 Okay, the activity of atmospheric carbon due to the presence of carbon-14 is about 0.255 becquerel. So this is the rate of reducing the number of nuclei per second, right? Per time, per gram of carbon. What fraction of carbon atoms are the carbon-14? That's the first question. The second question is that if the activity of an archaeological specimen, which is the object, okay, ancient object, is only 0.0637 per gram, what is its approximate age? So we need to determine the age of this ancient object. Okay. Before we go to that, we're going to need to find the total mass, which is denoted by capital M of the carbon-12. Let's go back to the Avogadro number for the carbon-12 isotope. We need to use the Avogadro number Na, okay, which is a fixed number, right? 6.022 times 10 to 23 atoms per mole, and times the atomic mass unit, atomic mass for carbon-12, which is exactly 12, and the amount of carbon-12, which is 1.66 0532 times 10 to negative 24 gram per unit. So this is the mass for carbon-12. After that, once you substitute the Avogadro number Na, 6.022, you're going to get 11.9999712, which is actually 12. Okay, so in 1 mole, we're going to have 12 gram for the carbon-12. So if you this is the unit for the conversion from atomic mass unit to the SI mass, right? SI system mass. If you pick up carbon 12 by 6.022 10 to 23 atoms, you're gonna get carbon 12 of 12 gram. Okay, this is from the standard. Okay, in standard, carbon 12 is around 12 gram per mole, and if you pick up only 1 gram of carbon 12, it's going to be 1 by 12 mole. 1 gram or 1 by 12 mole will have Na by 12. Only 5.018333 10 to 22 atoms. I'm wondering how we have the final test or final exam without a calculator, because what you can see here is the tedious decimal number. Okay, it has several digits. Okay, the number of carbon 14 can be found from the activity rate, right, which is number of carbon 14 will be 1 by lambda, which is the decay rate. And decay rate can be found from the half-life, which is ln 2 by half-life. And delta N by delta T is the amount of decayed nuclei per second, okay, which is available in this value, 0.255 becquerel. It means decays per second. The original formula has the minus sign because that's decay rate. Okay, and once you substitute everything, the half-life, which is 5,730 years, can be converted to second, because second is the typical time unit in the SI system. You convert it to days first, okay? 365 days per year. And in one day we have 24 hours, and in 1 hour we have 60 minutes. And in 1 minute we have 60 seconds, okay, we can count it. And ln 2 is ln 2, okay, we're gonna leave it like that. เราไม่ให้ใช้เครื่องคิดเลขเราจะไปต่อไงลอน2เนี่ยในการสอบผมก็ไม่รู้เขาเหมือนกันว่ากระทรวงศึกษาธิการเขามาตรวจข้อสอบเราหรือยังไงหรือว่าเขาไม่พอใจตรงไหนให้เครื่องคิดเลขไปมันคุณได้ประโยชน์มากไหมเนี่ยได้ประโยชน์จากห้องวิชาอื่นมากไหมไม่ใช่การคิดเลขใช่ป่ะหมายถึงวิธีของฟิสิกส์ไปอย่างเดียวใช่ป่ะโอเค and we're gonna have the decay, okay, which is 0.255 decay per second, and here you this is in the unit of becquerel, right? The not one nuclei, only 0.255 nuclei. Nucleus will disappear in 1 second. And once you compute everything, you're gonna get 6.647 times 10 to 10 atoms. Okay, this is the amount of atom for the carbon 14 at this rate. Now we can compute the ratio between carbon 14 and carbon 12. Carbon 14 first, okay, which is the main important target for us, and carbon 12. Okay, you just leave this number to this one. You can find that it's around million times, okay, or million fraction of the carbon-12. And the rate of the specimen, which is the ancient object, and the rate of the carbon-14. You know that carbon 14 has the rate of 0.255, okay, and the rate of the object which is available here 0.063 Sem in becquerel. Once you divide this number by the rate of carbon-14, you get 0.249. And we're going to leave it to the ratio here. The rate of specimen equal to rate of the carbon-14, and this is the half-life, right? One half. And the amount of half-life, the number of half-life is T. This is the time, right? Comparing to the half-life. Rate of the specimen is 0.26. This is the ratio we have already calculated, 0.249. You just leave it, and 2 raised to T divided by half-life. In order to find the variable T, you need to take the natural logarithm to this, and you're going to get ln 2 as well, and minus T by half-life. What we would like to find is T. You need to move the half-life to the left-hand side, ln 2 to the left-hand side, and the negative side as well. And ln 2 and ln 0.249 together with the half-life can be multiplied to each other. You're going to get the result in years, because the half-life is provided in years. 11,466 years, so that was quite a long time ago. Okay, this is very ancient object, actually. I don't know whether if you would like to work with the guy who just received the Nobel Prize in tracking the age of the human species. He's from Sweden, right? But he worked in the laboratory in Germany. If you want to apply to work with him, I'm not sure whether he would ask you about carbon dating, because this is one of the important features in order to track the trace of the human moving from one place to another place, and you need to know the age of the object, right? Once you discover skeleton or the bone of the human in the ancient time, okay. Okay, carbon dating is important for us to determine the age of the object, especially ancient object. But the world is changing, right? Because in the last 100 years, combustion engine and the combustion of fuel has a big impact to our atmosphere. The concentration of the carbon-14 in the atmosphere changes for a few percent during the last 100 years ago. During the last 100 years. This is because the burning of fossil fuel and atmospheric testing of the nuclear weapon can cause also additional carbon-14 and carbon-12. So the ratio might fluctuate or vary from time to time. But anyway, even there is a disturbance caused by human, with burned fossil or even the nuclear weapon test, you can correct the time somehow based on the data record from the history. Okay, now we arrive at the nuclear reactions. Okay, we are going to apply the decay process to human life, especially in terms of energy. Okay, we have seen the decays of unstable nuclei in terms of emitting, such as alpha particle, beta particle. Okay, sometimes both processes are followed by the gamma ray emission. Nuclear reactions are the changes of the nuclear structure by bombarding them with energetic particles. This process usually doesn't take place in nature. It's man-made experiment. In 1919, Rutherford bombarded nitrogen with alpha particle. Okay, he accelerated. He accelerated the particle, the alpha particle, to hit the nitrogen nucleus. Okay, from the alpha particle can be derived from any radioactive source. The process can be written like this. Okay, he has the new helium-42, and it moves with the energy. It hits the nitrogen-14. The result we get is the result he got is oxygen-17 and hydrogen. Okay, hydrogen-11, which is protium. This process is known as the nuclear reaction. That seems to be the first nuclear reaction that was successful in the human history. Let's consider the example about nuclear reaction in 1932, 13 years later, in England. Robert Chadwick bombarded beryllium with an alpha particle. Again, the most popular particle that is used to hit another nucleus is alpha particle, which is helium-42, and it hits beryllium in. Of course, you can see the 4 plus 9 will be 13, but the result takes place in terms of carbon 12. Okay, carbon 12 is the most general element around us. And of course, we have 2 protons and 4 protons. We get carbon, which has 6 protons. And another daughter nucleus is X, okay, with A and Z. So X is not any element, but it's unknown element to us. A is the number of nucleon, Z is the number of proton to this element or this nucleus. So what is the particle AZX in the nuclear reaction in equation 79? Okay, you know, in chemistry, you need to balance the process, right? The interaction from input side and output side. But in physics, especially in this chapter, you need to equalize or balance the number of protons and the number of neutrons so that you can find what the element is. Okay, we start with 4 nucleons and 9 nucleons in the input side, and in the output side we have only 12. So 4 and 9 will be 13. The remaining thing for A will be only 1, right? And 2 plus 4 will be 6. On the right side we have already 6, so that will be 0. So we have only 1 for A and 0 for Z. Okay, we get 4.9 minus 1 minus 12 and 2 plus 6 minus 6. So we get X10. What is that? What is this particle? It's neutron, right? Because it doesn't have any charge. It's not proton, but it's a part of nucleon. So this element, this particle should be neutron. Okay, the answer is neutron. Okay, I think this is one of the questions in the final exam. Okay, you don't need to use calculator at all. Okay, you just try to get the concept of proton balance and neutron balance, right, for both sides of the process. Now, if the initial particles A and B interact to produce final particles C and D, according to this one, okay, A plus B, and the output turns to be C plus D, which are completely different elements or nucleus or nuclei. The reaction energy Q would be the mass difference times the amount of C squared, the value of C squared. So total mass of nucleus A, total mass of nucleus B subtracted by total mass of nucleus C and total mass of nucleus D. If Q is positive, it means that the total mass decreases, okay, and the total kinetic energy increases. So mass reduces, and the mass difference is dedicated to kinetic energy. The mass is converted to kinetic energy. And this is the concept of E equal to mc squared, the famous formula by Albert Einstein, that the human used this formula to determine the energy we could get from the mass difference, okay? On the other hand, if the Q is reaction energy Q is negative, it means the total mass increases. So the total kinetic energy would decrease as well. Atomic physics อยู่ครับเป็นโอเค we are considering the computation of reaction energy Q โอเคมาถามแล้วก็ไปละโอเคผมบอกไปแล้วหรือยังว่ามันจะมีข้อกำหนดหนึ่งอะที่ E+ เขาบอกว่าไม่ให้นักเรียนไปนั่งเรียนอีกห้องนึงอะไรอย่างเงี้ยกำหนดว่าห้องหลับไม่ขายโปรแกรมห้ามหลับไม่ได้ผมดูชยุทธพลก่อนเห็นป่ะชยุทธพลนะครับสลบสลายนะครับมีความสุขเขามากนะครับอยู่ในภวังค์นะครับตามสบายครับโอเคQ can be either positive and negative, and the explanation is the following: total mass increases, so energy is converted to mass. The former reaction is known as the exoergic reaction in physics. Okay, exoergic. I don't know the root for this one. Exoergic. Ergic would come from energy, but exo, what does that mean? Outside, right? External, right?
The system release energy.
Yeah, to outside, right? Okay. Exothermic reaction is also possible to use to this process, but it's generally used in chemistry society. And the latter one, the second process, when the Q, the reaction energy Q is negative, can be known as endoergic. What does endo mean? I don't know. Endo, inside, right? So inside, we need the energy to be inside this process. Okay, you need to put energy to that, so that the kinetic energy would decrease. Okay. In chemistry, they're gonna call endothermic, right? Inside thermal, something like that, reaction. Now let's consider the first example about the calculation of reaction energy Q. We have lithium as the input, and we accelerate the hydrogen. To heat the lithium nucleus, in formal word, we're going to say lithium is bombarded by a proton. Okay. we hit the lithium nucleus by proton, and the result turns to be helium-42 twice. Okay, two nuclei of helium-42. And the question, of course, according to this topic, determine the reaction energy Q to this process. Of course, there is only one formula in 83. Mass of the input side subtracted by mass in the output side together with the speed of the light. Okay, square. Of course, input side we have mass of hydrogen, mass of lithium, and mass of helium-42. Okay. เนี่ยไม่ให้ใช้เครื่องคิดเลขแล้วผมจะออกข้อนี้ได้ยังไงเนี่ยมาก่อนใช่ป่ะมันไม่ใช่นะมันจะเป็นจำนวนของนิวเคลียออนไปเลยใช่ใช่ครับมันจะเป็นอินทิเจอร์ไม่ได้ไงค่าแมสจริงๆใช่ครับผมก็งงเลยกระทรวงศึกษาไม่ให้เราใช้เครื่องคิดเลขศิริวิทย์โพคิดจะออกข้อสอบอย่างนี้ครับศิริวิทย์โพคิดเขาไม่ให้ใช้เครื่องคิดเลขแล้วผมจะออกไงเนี่ย
1+1 เท่าไหร่ก็เป็นแบบวิธีคำนวณในช้อยแบบเอาไม่คำนวณตรงไหนวะ
ไปออกเป็นช้อยแทนใช่ป่ะแล้วก็ผมใส่เครื่องหมายบวกลบสลับกันไปใช่ป่ะแล้วคุณก็กาเอานะแจ๋วดีเนาะมันเอาแบบนั้นนะตกลงกันก่อนนะคุณจะได้ไม่ตกใจนะโอเคป่ะแบบนั้นนะผมก็ใส่เครื่องหมายบวกลบสลับหมายถึงว่าช้อยลงเลขไปเลยอย่างเงี้ยเหรอแต่ว่าไม่ต้องถึงคำตอบอย่างเงี้ยนะหรือว่าไงทีมศิลป์ว่าไงM42 หมายความว่าไงอันนี้นะเอาใส่ไปในช้อยเลยอย่างเงี้ยนะครับบรรทัดที่2นี้เอาแล้วแต่คุณอะเอาที่คุณทำได้โอเคปะเดี๋ยวมันแบบมันยากแล้วช็อกคุณเกินไปเดี๋ยวคุณก็จะบ่นว่าผมออกอาจารย์ออกข้อสอบยากเกินไม่ตรงตามเนื้อหาอะไรอย่างเงี้ยคือปกติอะผมจะให้คำนวณเลยปึ้งแล้วก็กาคำตอบสุดท้ายแต่รอบเนี้ยเขาเขียนมาว่าไม่ให้ใช้เวลาหมดแล้วครับขออภัยนะครับno still 10 minutes โอเคกลัวหมดเดี๋ยวคนถัดไปเขาจะมาว่าผมครับอยู่นานเกินโอเค you just leave the mass of the input side which is hydrogen mass of lithium okay and mass of helium-42 ถ้าคุณไม่ลงทศนิยมนะมันจะลบกันเป็น0เลยนะ1 + 7 เป็น 8แล้ว2 × 4 ก็เป็น8 8 - 8จะเป็น0นะแล้วมันก็จะไม่มีพลังงานได้เลยแต่ที่มันเกิดพลังงานเพราะว่าทศนิยมมันต่างกันนะครับโอเคyeah you get the mass success okay mass difference by 0.018 and you can convert it to energy by multiplying with the 931.5 okay you're gonna get 17.35 mega electron volt from this process so when Q is positive it means this process can take place in nature itself okay automatically so but with this amount 17.35 mega electron volt will be dedicated to the kinetic energy will be transformed into kinetic energy to the helium-42 the alpha both alpha particles they're gonna absorb that amount of energy to be kinetic energy they're gonna move with speed after the bombardment in equation 84 the total kinetic energy of the two separating alpha particles is 17.35 which is greater than the initial total kinetic energy of the proton and the lithium nucleus
Okay. Actually, proton and lithium would have also speed. Okay. And if you calculated before, the kinetic energy at the beginning would be less than the kinetic energy at in the final state by this amount, 17.35. Next, find the reaction energy for the Rutherford experiment in equation 78. Okay, let's get back to the first reaction process, which was done by Rutherford in equation 78. He bombarded nitrogen 14 with alpha particle, and the result will be oxygen 17 together with hydrogen. Now we're going to compute Q from equation 83 from this one, reaction energy. Okay, mass of helium alpha particle with nitrogen 14 subtracted by the mass of oxygen 17 and subtracted by mass of hydrogen. Okay, you just look at the table and leave this number to this formula, and mass of nitrogen from the table, mass of oxygen 17, and mass of hydrogen. Okay, you can see that you're gonna get mass difference, but mass difference here turns to be a negative quantity, negative number. And once you multiply it with the 931.5, you're gonna get the energy, which is minus 1.192 mega electron volt. Okay, so what does that mean when the energy is negative? It means that both input particles will lose the kinetic energy by this amount. Okay, the amount of energy by 1.192 is absorbed in the reaction, and they're going to have less speed for both particles. Rutherford reaction will take place if the total initial kinetic energy is at least 1.192. You need to accelerate helium the alpha particle by at least this amount. Okay. Otherwise, this process will not take place because the input energy is not sufficient. The endothermic, which is the process like Rutherford here, will not occur unless the incoming particle has at least enough kinetic energy to overcome the energy deficit. In order to break the nucleus, you should have enough kinetic energy. Otherwise, when the energy is not enough, the process as we expected in 78 will not occur. Okay, that's nuclear reaction, right? Let's talk about nuclear fission, which is a kind of nuclear process that we could have. Nuclear fission, of course, is the process that you decompose the big nucleus into two smaller nuclei. Unstable nucleus split into fragments. Okay, nuclear reaction is the process that is made by human, but nuclear fission is a process that takes place naturally in nature. Okay, we don't have to put energy to that. It's gonna break. It's gonna be broken down into two nuclei automatically. Unstable nucleus splits into two fragments or two smaller nuclei of comparable mass, and the ratio of two nuclei could vary. Okay, it's not a fixed ratio between the mass of the first object and the second object. In such a reaction, the total mass of the product is less than the original mass, so original of the heavy nucleus. So This is the not endothermic, exothermic, right? Exergic. Okay, when Q is positive. Okay, it's called exergic reaction or exothermic in chemistry. So nuclear fission is exergic or exothermic, right? The first nuclear fission process that was discovered by human in the history is in 1939 by Otto Hahn and Fritz Strassmann. They bombarded the uranium-235, which is the active, very active isotope of uranium. อะไรนี่สะเทือนมาถึงกำแพงหน้าจอผมด้วย uranium-235 with neutrons, okay, a small particle. Neutron, okay, comes with kinetic energy with a speed, and it hits uranium-235, turns to be uranium-236 with star. With star means it's in excited state. You know, it just increases the number of proton A, right? But it doesn't change the number of protons. So it's still uranium, and it's going to be broken down into two smaller nuclei, or sometimes they call fragments. Okay, and N, the number of neutron, together with the mass of the neutron, okay, number of neutron. Uranium-236 with star with 92 is an intermediate state that lasts only for about 10 to negative 12 seconds. Okay, so it's very short, picosecond, right? Uranium-236 just lasts only 10 to 12, 1 picosecond. And after that, it's going to be broken down to two nuclei, two smaller nuclei, together with neutron. In this process, you can see that you can get the gamma ray easily, okay, from this process, because it's in excited state. Well, X and Y are daughter nuclei from splitting the uranium-236. NN is the number of neutrons you're going to get. And if you control the neutron, okay, if the neutron here, the neutrons here, hit another uranium-235, it's going to be broken into two smaller nuclei later. Okay, the time is over. I need to pick up all the stuff to another section. See you on Wednesday. If you have any questions, just raise your hand. If not, see you on Wednesday. Bye bye. สวัสดีครับ on Friday. Sorry. ครับ สวัสดีครับ ครับ
วิดีโอกำลังเอาเข้าไปใช้เสร็จทำไม
นะครับขอฝากอันนั้นไปหน่อยนะไปห้องนู้นนะครับกล้องฮะอ๋อเซ็นสมุดอันนี้นะครับได้ครับของตอนเช้าด้วยวันไหนเอ่ยที่มีส้มแตะไว้อ๋อแปะไว้วันนี้นะครับหลักการ3นี่นะครับ นี่นะโอ้ใช่ครับ มาคุณเปิดแกลเลอรี่ตัวเองด้วยนะครับก่อนฝีมือการวาดภาพสวัสดีครับ เอาแล้วอาจารย์เขาไปอยู่ห้องคุณ
เขานั่งคุยกับคนหน้าห้อง3 คนครับ
อ๋อ
เขารออาจารย์เข้าไปคุยครับ
อ๋อโอเคผมประทับใจแว่นกัสซิเดตมากเลย ชอบ ซื้อได้ที่ร้านไหนครับเนี่ย
ผมซื้อมาจากต่างประเทศครับ
ต่างประเทศ
สั่งมา
มีหน้าไม่หาเจอได้ในเมืองไทยเลย
ผมเจอคนทักทุกวันครับผมยังไงเมื่อวานมาครับผมกลับบ้านแล้วอาจารย์ที่9
กลับบ้านแล้วเหรอโอ้รั้วโรงเรียนยังไม่เปิดเลยครับ
เปิดแล้ว8 นาที
อ๋อเปิดเลยตามสบายครับ ตามสบายชิวๆอ๋อตามสบายไม่เป็นไรครับอาจารย์ตามสบายเลยครับ ตามสบายเลย ผมไม่รีบครับ